if something is growing exponentially, it will eventually grow faster than almost any other type of growth. If we return to the number of cells example, and that information is actually presented in this graph here. On day 1, we had 2 cells, then 4, then 8, then 16, then 32, then 64, and it's off the chart after that. So how many cells will there be on the 10th day? So I'm going to show you on the calculator that we can start with, on day 6 there was 64 cells. So let's put 64 and enter. That's day 6. And then if we say answer times 2, then we will have the day 7 answer, enter, and then enter. So this is day 7, day 8, day 9, and day 10. So on day 10, there will be 1,024 cells in that culture. And this is how I recorded it here. I put down the number of days and then how many cells all the way up through day 10. How long until there are 1,000,000 cells? So even though that seems like a ridiculous question, it might take a super long time. If we just keep counting, it's not actually that long because exponential growth is so strong. So this was day 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There it is. Day 20, we exceeded 1,000,000 cells for these cells that are undergoing mitosis. So I wrote down 20 cells. And the way I did it on Desmos, many scientific calculators can also do that same process, and you're welcome to ask me for help if you want on how to do that. In theory, the numbers can keep doubling forever, but in real life, conditions can limit growth. Cells could run out of space or run out of food. So it is unlikely that this exponential growth would continue forever. Now remember that this was cells that were doubling every day, so that's a 100% increase every day. The next problem we're going to look at is Eugene's population growth. So Eugene was about 169,000 in 2017, but it isn't always growing the same percentage every year, so it's not a perfect example of an exponential growth model, but it is close to about 2% each year. So we're going to model this as if it was a perfect exponential growth situation, and I want to show you what this would look like for Eugene. If Eugene grows by 2% in 2017, we need to find 2% of 169,000. So to do that, we would take 0.02 times 169,000, and that gives me 3,380. And then, how did I get this number? Well, you take 169,000 plus 3,380, and that gives you 172,380. So I'm going to clear this. 169,000 plus 3,380 gives me 172,380. And again, 0.02 times 169,000. That's how I got the amount of increase, which was 3380. So put that number in this table. And now I want to teach you a shortcut. So instead of doing this in a two-step process where we multiply and then add, I want to teach you a one-step process. The shortcut is to multiply by 1.02. 169,000 times 1.02 immediately gives me the next year's population, 172,380. The reason we multiply by 1.02 is because we're going to have 100% and 2% extra. So 102% is 1.02. So I take every year and I multiply by 1.02. That answer times 1.02. Over and over again, we're always multiplying by the same number. And in this case, it's 1.02. So we're not doubling every year. We're multiplying by 1.02. But that creates an exponential growth situation. And I'm going to show you that when we do this math, we can round to the nearest whole number, but we can leave the decimal number in the calculator to work off of. So after I get that answer, I can say answer times 1.02, enter, and that will round up to 175,828. And then I just keep hitting enter. That rounds to 179,344. Enter. 182,931. So there it is. And then just one more, 186,590. 186,590 if we round. So that's correct. These are all the Eugene population growths for 2017 through 2022. And it makes sense to round to the nearest whole number because these are people. How many years until Eugene's population exceeds 200,000? So we can go over here and keep counting. This was the 2022 number. So 2023, 2024, 2025, 2026 is the year that we exceed 200,000. And if we're in 2026, that's 9 years from when we started this problem in 2017.